bicarbonate's not a strong acid, so we just leave this alone. It just stays together. The hydrogen doesn't break off easily in water. If I have something stronger than water, it's possible I can pluck off hydrogen off. So this sodium bicarbonate with, what were we reacting with? Lithium phosphate? Formula for lithium phosphate is what? Li3 PO4. This is aqueous, and so I'm going to get lithium ions. I'm not going to balance it because I'm just interested in the species. So I have lithium ions and phosphate ions present. And there's one more major species present. It's a little tricky, but what is it? One major species is missing. Can you figure out what it is? It's pretty tricky because aqueous means water, and so water. So we got sodium ions, bicarbonate ions, lithium ions, phosphate ions, and water present. All right, step 1's inventory. Step 2 is we identify ID acids and bases using the chart. And so I'm going to use the acids chart to identify. So sodium ions. Do you see these on the acid and base chart? Acids on the left, bases on the right. Do you see them anywhere? No. So they aren't there. We're going to call these neutral. And then we go to bicarbonate. Do you see bicarbonate on the chart? Do you see it? Yeah, I see it. It's right here. See that? And so this side is acid or base? That's acid. But bicarbonate is tricky too because bicarbonate occurs here on the left side. It also occurs here on the right side. The right side is base. And so something that can act either as an acid or a base is called amphoteric. And so bicarbonate's amphoteric. And so it can react either as an acid or a base. How it reacts depends on what you mix it with. You know, sometimes it acts as the acid, sometimes it acts as the base. It depends on what it's mixed with. We can figure out how it's going to act in this case, whether it'll act as the acid, base, or neither. So sodium ions are, I guess, neither. Another word. Lithium ions. Are they acid? Are they base? No. So we can say neutral or neither. Let's call it N. Phosphate ion. Phosphate doesn't occur on the acid side. I mean, we need the hydrogen. There's no hydrogen on phosphate. Phosphate just occurs on the base side. So phosphate is a base. And then water. Water occurs on the acid side here. Not very good. And water also occurs on the base side. Scroll up here, we can see it. So it's on both sides. It's on both sides, it's an acid and a base. It's amphoteric. right, what do we do next? Step 3, find the strongest acid present. Okay, we have two acids, bicarbonate and water. Which one is stronger, bicarbonate or water? So when we look at the chart, here's bicarbonate, here's water. Which one's stronger? Bicarbonate stronger. And so the strongest acid present here is bicarbonate. Therefore, it's going to dictate how it behaves. It will behave as the acid. Step 4. Find the strongest base present. And so we have three bases. We have bicarbonate, we have phosphate, and we have water. The strongest base is down here on the right. So we go up. The first base we hit is phosphate, right here. The next base we hit is bicarbonate here. And then water is way up there. And so which of those three is the strongest? Water? Well, this chart is inverted. The strongest on the right side is at the bottom. The weakest is at the top. And so it turns out that whichever one's closest to the bottom here, which would be phosphate. Strongest base. So, I forgot. Base. So phosphate should act as the base. And so what we do is, the strongest acid will react as the acid, the strongest base will react with the base. So even if it's amphoteric, you can tell how it's going to behave depending on what it's mixed with. Step 5. What we're going to do here is we're just going to react the strongest acid with the strongest base. By basically we're just going to transfer a hydrogen ion between the acid and the base. So an acid is a H plus donor. And then the base is an H plus acceptor. And so the acid's going to lose an H plus. That's going to leave me with CO3. And the base is going to gain an H plus. That's going to leave me with an HPO4. So I just moved the hydrogen. But it's not just a hydrogen, it's a hydrogen plus ion. So bicarbonate loses an H plus. What's its new charge? Or what's the charge on carbonate? Be 2 minus. And then if phosphate gains an H plus, what's its new charge? Yeah, 2 minus. These are the potential products. These are the most probable products. However, we don't know if it's going to react. Because in order for a reaction to occur, what do we need? We need something. What we need is a driving force. And so, step 6, determine if driving force is present by identifying the acid and base in the reverse reaction. All right, what I mean by this is we're going to write down this bicarbonate plus phosphate yields carbonate plus hydrogen phosphate. We know what the acid and the base are going forward, but we want to figure out what it is in the reverse direction. So what I'm going to do is I'm going to go to the products and then go backwards. If I go backwards, then what happens to carbonate? Going backwards, carbonate gains an H+. If carbonate gains an H+, that's what we call the base. And hydrogen phosphate loses an H+ going reverse. So we're just going to go backwards. And so if we were to reverse this reaction, the base would be carbonate, the acid would be hydrogen phosphate. We could go backwards. Step 7. If we go from stronger acid and stronger base to weaker acid and weaker base, then this is driving force. If we go from weaker acid and base to stronger acid and base, then we expect NR, no reaction. So what we're going to do is we're going to compare the two acids and the two bases. All right, let's compare the two acids here. Bicarbonate versus HPO4 2-. Which one is a better acid? We can see it here. Here's bicarbonate. Here's HPO4 2-. Which one's a better acid? Well, we have to kind of orient ourselves. Where's the strongest acid? At the top. So which of those two acids is closer to the stronger or strongest acid? Bicarbonate. And so it turns out that bicarbonate is stronger. It's not strong. It's stronger than hydrogen phosphate. Still weak acid. But bicarbonate's slightly stronger than hydrogen phosphate. Let's take a look at the bases. The bases would be carbonate versus phosphate. Which one's stronger? Phosphate's stronger. So we have two bases here, and we're going stronger to weaker here. Therefore, we're going from stronger to weaker. We see driving force, and we have reaction. Acid-base reaction should occur. Now, if we went from weaker to stronger, then the opposite direction is favored. That is, the reverse reaction is favored. In this case, the forward reaction is favored. We want to go from stronger to weaker. No matter which way we have it written. Okay, let's do another example together. try sodium chloride and sodium sulfide solution. Actually, I'm going to do this. I'm going to do aqueous sodium chloride with solid sodium sulfide. I'm going to mix these two together. What's the formula for sodium chloride? NaCl. And sodium sulfide? Na2S. Alright. This is aqueous. This is solid. So if I have aqueous sodium chloride, what's the inventory? I have sodium ions and chloride ions. The water is going to tear apart that lattice, make the ions. How about sodium sulfide? When I mix these two together, I'm going to have water present. And what happens to the sodium salts? Do the sodium salts dissolve in water, or are they insoluble in water? They dissolve in water. So if sodium sulfide dissolves in water, what forms? Na plus and sulfide. So I have Na plus and sulfide. Because sodium salts will dissolve, and that will dissolve in the water that's already present in the sodium chloride. Is there anything else? I don't have to write sodium twice. I have sodium ions, chloride ions, and sulfide ions. Is there anything else? Water. All right, this is the inventory, what I expect to find. Then we're going to identify sodium ions. Are they acid? No. Are they base? No. None of the above. Chloride. Chloride is kind of tricky because when we look at the chart, it is well, acids are on the left, bases are on the right, so it's a base. But this base is, in fact, all of these bases here about water, this base is weaker than water. Weaker than water. And so let's say you ran out of antacid. If you ran out of antacid, can you use like a table salt instead, sodium chloride? Will sodium chloride help neutralize your stomach acid? And the answer is no, you're better off just drinking water. In fact, chloride is so weak, it's not considered a base in water. Chloride is too weak to be considered a base in water. So that's why I'll put a little asterisk here because it's incredibly weak. So like sodium chloride, we typically think of as not being a very effective base or very effective antacid because it isn't. It's pretty much neutral. Okay, sodium ions are the same. Sulfide ions. Sulfide ions would be strong base. But here I'm not, the only time I'm going to put something is with that chloride nitrates, that kind of stuff. Water, it's an acid or a base. It's weak both ways, but can act either way. Okay, so I've identified the acids and bases present. What's the next step? Well, I need to pick the strongest acid. Well, I only have one acid, so I don't have any choice. What's my acid? Water. Only acid present. I have 3 bases present. Out of those 3 bases, which one is strongest? Take a look at the chart. The strongest base is down here, methyl. So it looks like sulfide is the strongest base present. And so the reaction should be between the acid water. Water is normally amphoteric, but depending on what you mix it with is going to dictate how it behaves. So in this case, it's going to be the acid. What do acids do? They lose an H plus or give an H plus to the base. Base is accepted. And so what forms? Well, do we transfer both H pluses or just one? Just one. And so if H2O loses an H plus, then we're just left with OH. What's the charge? Minus. And then if S2 minus gains an H plus, we're going to form HS. With what charge? Minus. So it's an H plus. It's transferred. And so we pick the potential products here, but we don't know if we're going to get those products. What has to be present is a driving force. So let's figure out what the driving force is. The acid, water, the base, sulfide going forward. Now what we're going to do is we're going to go backwards. When we go backwards, what's the acid, what's the base? Hydroxide loses a hydrogen going backwards or gains a hydrogen going backwards? Gains. So hydroxide gains a hydrogen to go to H2O. If it gains, is it the acid or the base? It's the base. And then HS minus loses or gains going backwards? Loses, so this has got to be the acid. Now let's compare the 2 acids. We compare the 2 acids, water versus HS minus. Which one's stronger? Water versus HS minus. Which one's stronger? Water. Sulfide versus hydroxide, which one's stronger? Base. Sulfide. So we're going from stronger, stronger to weaker. Going from stronger to weaker, this is our driving force. So we expect reaction to occur. Expect reaction. If we went from weaker to stronger, we get no reaction. If we get no reaction for acid-base, there's still one more reaction type that could be. What's the final type of reaction that we might look for? Redox. Third reaction type is the redox reaction, of which there are some subtypes, subcategories. The first subcategory of redox is the element plus element combination reaction. Look at some examples. Magnesium. The element magnesium is in these solids of metal. Plus oxygen, gas, O2 gas. If If we combine these two elements, what compound do we make? Well, magnesium goes to magnesium 2+, and oxygen goes to oxide. So we should form MgO, magnesium oxide, solid. We did this reaction in the lab. To balance this, I'll need half an O2, or double everything. If I double everything, I'll get 2 magnesium solids plus an O2 gas yields 2 MgO solids. Here I'm going to write in all the states, solid, liquid, gas. So this is an example of an element plus element redox reaction. Magnesium loses electrons to form magnesium 2+. Oxygen takes electrons. So magnesium is what we call a reducer. Oxygen is a oxidizer. So oxygen is the oxidizer. It takes electrons. Oxidizers take electrons. Magnesium is a reducer. Reducers lose the electrons. So we have a redox reaction here. Magnesium forms a fixed charge. Sometimes we have variable charges that come up, like copper. Let's look at copper plus O2, the oxidation of copper. What are the common charges for copper? Plus and plus 2+? Yeah. +1 and +2. So if we partially oxidize, we call this partial oxidation, we form copper. Is it copper 1 oxide or copper 2 oxide? Can you name those? Yeah, copper 1 oxide on the top, copper 2 oxide on the bottom. Copper 1 oxide has a +1 charge, copper 2 oxide has a +2 charge. We would call, we call formation of copper 1 oxide incomplete. This is copper 1. This is an incomplete oxidation. It's incomplete oxidation because copper can lose 1 more electron to form copper 2. Copper 2 would be complete oxidation. S, yeah. Both of those are S. Both of those solid. This is interesting. Here's the gradual oxidation of, it looks like copper penny here. You see the new pennies, the color, orange? And what happens? It gets darker and darker. The green is a different thing. I'll talk about that later. And so what I'm going to show is I'm going to show what copper 1 oxide looks like. This is copper 1 oxide. See the color? It's kind of a red color to it. You may also like this. You know what this is? This is copper 2 oxide. So copper 1 oxide is red in color. Copper 2 oxide is black color. Both of these are solid. And so what happens is this, with the penny, at least. Looks like with a penny we go partial oxidation here, not complete, but partial. So the copper penny goes from kind of an orange color to a red-orange color to eventually a black color. And so it's going from copper metal to copper 1 oxide to copper 2 oxide, and then it stops because that's what we call complete. It's like iron. What are the common charges for iron? Plus what and plus what? Plus 2 and plus 3. So when iron rusts, it could be partially oxidized to iron 2 oxide, or it can be completely oxidized to iron 3 oxide. And so let's take a look at rust. What color is iron 2 oxide? Can you tell? Iron 2 oxide is black. Is that what rust normally looks like? Rust is normally black? No. What color is iron 3 oxide? Red. And rust is normally a red-orange color. And so for rust, initially when iron starts to corrode, we might get a black coating on it, iron 2 oxide. Eventually the iron 2 oxide is going to convert into iron 3 oxide and create this familiar color of rust. And so when we have variable charge, it's a little bit tricky because we have variable products. Here we only have one product because there's only one charge on magnesium, it's 2+. Over here there are two potential products, copper 1 oxide or copper 2 oxide. The same thing with iron. There are two potential products, iron 2 oxide or iron 3 oxide. Looks like iron 3 oxide is much more prevalent. So what we're going to do is we're just going to do complete. Normally we'll just do complete oxidation. So, eventually those pennies are going to rust, not rust, but corrode. Be oxidized all the way to black copper 2 oxide. The green color there is something a little different. We'll talk about later. The green color is for reaction, something else. All right, so that's element plus element combination reaction. B is the complete combustion of CHO organic. Organics that contain carbon, hydrogen, and potentially oxygen. It doesn't have to contain oxygen. So an example of this would be methane. When we react methane, methane's a gas, what should we form in the complete combustion of methane? CO2 and H2O. Let's balance this. We can't balance by ions, we have to balance by atoms. So one carbon, 4 hydrogens. I'll need 2 waters. 4. And this gives me 2 plus 2 is 4 oxygens. I'll need 2 O2s. CO2 is a gas. That's complete combustion. We could have incomplete combustion of methane. Do you know what we form when we have incomplete combustion? Carbon monoxide and water is always formed. whether it's complete or incomplete. Carbon monoxide and this is black. Black. We did it in the first lab. Soot. So incomplete combustion is when we don't have enough oxygen. When we don't have enough oxygen, we form carbon monoxide and soot particle. Remember the Bunsen burner lab? What was it? And so what we're going to do is we're just going to assume that we're going to get complete. Otherwise, we have multiple products that form here as well. And so for all of these, we'll just react it all the way. That way we don't have to deal with multiple products, but you should understand that multiple products are possible. Especially when the charges vary. I mean, carbon's charge varies from -4 all the way to +4.
What's the
Soot chemical formula is carbon solid. It's like charcoal.
Okay.
Charcoal is a mix of amorphous carbon. You know what amorphous means? Amorphous is non-crystalline. It's kind of disordered. And graphitic carbon. It's a mix. This is incomplete combustion. This is incomplete combustion. We can have a carbon hydrogen containing compound, or we could have a carbon hydrogen oxygen containing compound. So let's try this one. Let's try C6H12O6. Solid. This is glucose, which is sugar. If we burn sugar completely, what does it form? Well, we burn it in O2, and it should form. They're all the same product. They're going to form CO2 and H2O. So we have 6 carbons here. That means we're going to need 6 CO2s. We have 12 hydrogens here. We'll need 12 hydrogens here. So we'll put 6 waters there. And then how many oxygens? Well, on the right, I'll count them. 6 times 2 is 12. 12 plus 6 is 18. I have 18 oxygens. So 6 plus 12 oxygens will give me 18. 12, if I put 12 here, it's not going to work. I have to put 6 there. 6 times 2 is 12. 12 plus 6 is 18. So now it's balanced. O2 will be a gas. So this would be the complete combustion of glucose.
If it's combustion, is the H2O
H2O, a liquid. During the combustion process itself, it's steam. But the funny thing is it going to stay steam forever? If it stays steam forever, then we leave it as steam. But will it stay steam forever? No, because eventually what's going to happen is after it burns, it's going to cool back down. When it cools back down, it's going to turn into a liquid. And so what in the life of the methane, is it mostly steam? Let's say after 10 years after you burn it, is it still steam or is it liquid? You know, out of the 10 years after the reaction has taken place, what do you expect the water to be? Liquid. And so we put liquid here. Now, that's me. Your book, however, will put gas. It puts gas, but you know, gas is fleeting, you know. Gas is it'll be a gas for a minute, a couple of minutes before turning into liquid. And so it depends on the timing. There's another reason I put liquid there too, and I'll talk about that more. The other reason I put liquid here is because when we combust something, we usually try to get energy. If we combust methane, we try to get energy or heat. When we combust sugar, we try to get energy from that. The process of steam going into liquid water, that process releases energy. And so when steam condenses to water, energy is released, and we can capture that energy and do stuff with that energy. And so that's another reason why we go to liquid. That's complete combustion. Okay, the next type of redox reaction that we're going to look at is something called the single replacement reaction. Single replacement reaction has this. It's an element plus a compound. So if we take an element plus a compound, A plus BX, we expect to form AX, a new compound, AX plus an element here, A plus BX builds AX plus B. Oh, I'm almost out of time. So I'm going to abbreviate this. Basically, the advantage of single replacement is the pattern is simple. Simple pattern. The disadvantage is the pattern is simple. The pattern is simple. Disadvantage means that there are lots of exceptions. And so, lots of exceptions. If there are no exceptions, that's great. It's pretty easy to do. Let's do an example of this. Zinc solid plus hydrochloric acid. Here, so I have an element, the element zinc metal, and I have a compound, hydrogen chloride, which makes hydrochloric acid in aqueous solution. And so this is my A plus BX. Okay, A plus BX yields AX, the compound plus B. AX would be the zinc. What is zinc's charge? What are the common charges of zinc? 2 plus. Just 1? 2 plus, 3 plus? Actually, zinc is fixed charge. There's only one charge of zinc, and it's Zn2 plus. Chloride is a Cl minus, so the correct ratio would be Zn Cl2. So we're going to form zinc chloride, AX plus B. The element is H, hydrogen. But is H stable as single atoms? No, and so we're going to have to, if we form single atoms of H, they're going to combine to form diatomic molecules of H2. And so the pattern is simple. A plus BX equals AX plus B. Then we look for the driving force. The driving force is something called the activity series. And so, we get reaction if we go from more active element to less active element. If we go from less active to more active, then there's no reaction, there's no driving force. So let's take a look at the activity series. This is the activity series here. And at the top of the activity series is lithium. Lithium is the most active element here. And then it goes down in activity. So lithium is the most active. So what we're going to do is we're going to compare the two elements. The two elements are zinc and hydrogen. So we're going to compare A and B. So we go over here, here's zinc here. I don't see hydrogen up here. It must be down. Let me scroll down here. There it is. So here's zinc, here's hydrogen. Which one's more active? Lithium's the most active at the top. Zinc. Zinc is closer to lithium than hydrogen.
You're not getting a periodic table on the test
You are getting a periodic table for the test. Yeah. Periodic tables are available. This,
Tell that.
no, you can't. You can't tell this from the chart you have, but we aren't going to do redox, I think, for this test. We're just going to focus on metathesis and acid base for this test. Redox we'll do later in the next test. We'll have redox. Redox reactions are more involved. And so there's a reaction here. In other words, we go more active to less active. But you do have, I'm giving you the activity series on this chart. The activity series is going to come here. This is the chart you're going to get from for the exam. And if you look at this chart, take a look here. Do you see what we have here, down here on the bottom right? Lithium. So this is the inverted activity series. Lithium is the most active. Here's zinc. Here's hydrogen. Zinc is more active than hydrogen because zinc is closer to lithium. Lithium is the most active.
Hydrogen less active because it bonds to itself.
That's not the reason. We'll talk more about the reason why hydrogen is less active. But it's not because it bonds to itself. Because lithium bonds to itself also in the lattice. When we look at lithium metal or zinc metal or any metal, metals form a lattice like this, and all the atoms are bonded together. For lithium and zinc, they're held together by what we call metallic bonds, which we'll talk about here. All right, I'll stop here.